Hi, I'm Saeedul.
And I'm Liam Cline.
So let's start this. In late 2006, Given Imaging released PCCam colon, which allows for accurate imaging of the ileum, a common site for early onset Crohn's disease. Small form factor requires low computational complexity compression algorithm to keep power consumption and memory buffer requirements down. Dr. Tariq Khan proposes a three-part algorithm to reduce file size, consisting of luminance-chrominance conversion, reduction of spatial resolution of color channel, which takes advantage of the human ability to discern color difference better than intensity differences. 2. Taking the difference between adjacent pixels, which takes average advantage of the fact that most areas of an intestine are approximately the same color and intensity. 3. Dividing each pixel value by an optimally selected number yielding an integer quotient value and integer remainder value as one would obtain using long division. These two values are encoded side by side in a serial file output using an array and binary respectively. In our MATLAB program, we implement Khan's algorithm with success. We tested the program on 150 corner-clipped endoscopic images from an online database and compared benchmark values favorably with those obtained by Khan. The program we wrote consists of a single file. To ease understanding of the code, we breakpointed key points in operation.
Alright, so now I'm going to walk you through our code. So here's line 11. So Khan optimally selected 812 as the subsampling rate. So every 8th pixel is sampled in every odd row, and every 4th pixel is sampled in every even row. Next, we query the image metadata, initialize an output table for benchmark values. Since Khan's algorithm is optimized for 8 bits of information per channel, we reduce the bit depth if necessary. As per the formula defined in Khan's paper, we build a matrix for scaling and vector for shifting to convert from RGB to YUV color spaces. Next, since the output spatial resolution differs for Y channel, odd row C, and even row C, we required 3 separate matrices, which was a little bit difficult to code. Next, sample pixels are fed into the YUV color space matrices. And then, since YUV subsample is the only lossy portion, we converted back using the inverse of the previous portion just to get benchmark values. So next we do pixel by pixel error count, power signal to noise, and a custom created visual signal to noise ratio. And those are kind of our point estimators. So then next, the part 2, taking the difference between adjacent pixels, we're doing it in 3 steps. So the first pixel is our seed. Then we go down the first column and take vertical differences, and then we do the rest of the image using the vertical column as seeds for each row, horizontal differences. And then third, the Gulam-Rice encoding is probably the most difficult one brain-wise to code. So we set some comments here, or constants here, to determine values to divide each pixel by and the pixel magnitude maxes. Next we define some stop points for the lengths. And then we map negative numbers to odd positive numbers and positive numbers to even numbers by multiplying them by 2 with the absolute value. So then we do the quotient, we compute that, and compute the number of bits required to encode it, add that to the allocation for file size, and then we do the remainder. So the process is repeated for the odd and even color channel rows. You can see in that for loop, it's exactly the same, just for the different channels.
The next part is performance evaluation. So in line 239, here you can see the file size is determined as a sum of quotient size and remainder size blank file space allocated. Next, the file is encoded by the first checking if quotient is too long for an array encoding. If so, encode escape character in an array followed by quotient in binary. Else, encode quotient in an array. Finally, the encode remainder in binary and add to file. Increment file cursor. And the last, once the file is encoded, the benchmark states are computed for the final file size. All states are outputted in a table row which the batch mode will be appended to a spreadsheet. In 300 lines of code, we produced a readily benchmarkable implementation of Khan's algorithm. It should be noted that the computational complexity of our implementation is significantly worse than Khan's low-level C implementation, so our code is not market ready. However, our code is likely much more user-friendly and readable thanks to the high-level universal acceptance of MATLAB in the scientific and engineering community. We see our solution as a means to test whether or not the algorithm is suitable for endoscopic images. Simply by changing constants, one can test parameter on different images to simulate what would work best on an embedded setting. Thank you so much for listening to our demo. We hope it was informational, educational, and enjoyable.